thirdly, more of the stuff you'll see here in intro psychology looks at subdivisions of the brain. And of course, we'll get to these. This is an overview period. Large anatomical subparts of the brain. It's possible, it's not the case, it's possible that the brain is like a piece of cauliflower. I wanted to use in the book a picture of this. Online, you'll find a picture of a skull with a cauliflower stuck into it, but I was advised against including that in the book for lack of educational value, I suspect. Material like a cauliflower is homogeneous. So if you go into any part of it, it's like any other part. There's some term for this in biology where the parts are all, they're not differentiated. So it's an undifferentiated thing. It's just a big lump of stuff. It's conceivable that the brain is like that it's a bunch of stuff with no particular parts. However, there are distinct parts. If we were doing an anatomy of the brain, if we had 100 brains to hand out, you can't miss it. And I'm sure you've seen enough pictures of the brain that you can imagine this. There are distinct anatomical parts of brain, including an entire left-right division in which the parts of the brain essentially replicate themselves, essentially without exception, on both sides. And those sides then are themselves massively interconnected by neural systems that connect the left and right hemispheres. That comes from these EEG technologies. The brain has these two halves, as I said earlier. They aren't really split apart like they just were, but you could, if you had a brain here, pull them apart a little. The left and right hemispheres. Somebody who's not far away, a neuroscientist at the University of Wisconsin-Madison named Richard Davidson, ran a whole series of studies that work every time, even though nobody expected them to work every time until he ran them. He found that different sides of the brain are more active during positive as opposed to negative emotions. More technically, they're differently active during emotional states that involve moving towards something that's attractive as opposed to away from something that's threatening. What he does is to run studies in which people show up in the lab. You can also run these with people who are depressed or not, and you get a similar result. And he creates positive and negative emotional states in a quite simple manner, like he shows humorous videos, a disgusting video, a sad video, and does it while the person is wearing these EEG things, which, as you noticed on that hat, have a lot of channels, a lot of recording stuff on both the left and right side, so you can then tell across time, before and after the person sees the disgusting or the humorous video, which side is more active. And quite routinely, there are hemispheric differences, with the right hemisphere being more active during positive emotions and the, oh my God. Fortunately, I remember my acronyms, which are LP and RN. And the acronyms have come to the rescue, unless that's wrong. But the acronyms have come to the rescue. The left hemisphere more active during positive and right during negative emotions, which is spelled that way in brain science. This was kind of a surprising thing and is a highly reliable finding. Another way EEG is used is in the stuff on consciousness. If you want to learn when things become conscious in the brain, it happens really fast, like if there's a small flash of light and you notice it, something happens in your brain within about 3 to 4 tenths of a second. The only way to learn what happens, because the third technique I'm going to put up is too slow to show you what happens, you need something that records really fast, is through these electronic recordings that can give you information every millisecond and show this kind of cascade of activity that occurs specifically when you notice something new as opposed to you missed it. If you retrieve those memories, it's not the case, noted, it even says not here. It's not the case that they're just stored like putting, you know, some electronic storage device on a shelf, and the shelf is the temporal lobe. That's not what the temporal lobe does, not because there's some other place. There isn't a single place. It just doesn't work that way. The way it generally works is that if you recall, I actually wrote this out. I must say this is one of the more important individual factoids about the brain. If you recall some event, it is not the case that there was some part of the brain that was the videotape or whatever electronic storage device they're using in the 21st century for storing the material. Instead, what happens is that there's a coordination among multiple parts of the brain. So there is, in a sense, an instruction for recreating the experience. The instruction is in the temporal lobe towards the end, so it's called the pole. But what happens is through these wirings of parts of the brain that are not shown here but that we had up last time, the temporal lobe can coordinate different parts of the brain, and so different parts of the brain will take part in the recreations of the sounds and the motion and meaningful social actions. No coincidence, it related to the motor cortex. And if you do the brain scanning, in other words, of somebody who's remembering what we did on the 4th of July, there is no little 4th of July place. What there is a coordinated multiple parts of the brain that essentially are doing kind of like a recreation of the event, as if there were little video systems and social meaning systems that all had to run pretty much in synchrony, and you need the temporal lobe to pull off that synchrony. Again, more fun for me than you, perhaps, but these are all things that seem straightforward now, and quite seriously, you know, the first time I taught this course, back in World War II, this would all be news. This was not the standard understanding. Now, to make matters worse, all those lobes of the brain come in pairs. There's two of everything. Because the brain, like you don't know it already, has sides or hemispheres. So the brain has these two sides. You know, almost everything biologically is bilaterally symmetric. And the brain is no exception. The sides are super highly connected. The word for these axon connections from one side of the brain to another is the corpus callosum. And then one day, some people realized it would be great fun if we had scissors and could cut the corpus callosum. Why not? This, again, was not one of those studies where you signed up for the wrong experiment and didn't notice on the consent form that it said, we may cut your corpus callosum. But instead was another one of those epilepsy, trying to stop the flow of electrical signals from one side to another. And it works. You could cut the corpus callosum. If you do that, I suspect, how many people know what happens? You know, these, are they in the popular lore, split brain experiments? Oh, good. It is not the case for those of you at home that all the hands went up in the air. Yes, I know there are various reasons for that. But one is that everyone was listening and does not know this already. What happens if you split the brain in two? Well, there's certain possibilities. One, of course, is that. I mean, that's quite possible. You know, if you decide, well, for fun, we'll split the heart in two and see what happens, it's not going to go well. And the brain seems like you need that too. It's quite possible. I mean, it must have been kind of a, so to speak, stab in the dark the first time people ran the study. They actually, frankly, there were studies like this before humans. The original person who does this, Roger Sperry, who has a Nobel Prize for the following sets of discoveries, and then works with somebody else. You'll see on a film in a minute. They do have non-human model experiments. They're not really just like, oh, I wonder what will happen here. Another possibility is the person will hugely lose mental abilities. Frankly, before these experiments started, if you did a survey, I suspect a lot of people would have expected this. And in fact, it still seems quite reasonable. Since there are so many connections among the brain, you could imagine the person dropping from, you know, 110 IQ to 10 IQ if you cut these connections. Instead, or, as I put it when making up notes, there could be some really weird thing that it's hard to anticipate, and it turns out there is. There's some really weird thing that's hard to anticipate. And here it is now. I don't mean to say this person is weird. Everybody who has this surgery to stop epilepsy from occurring has this kind of thing. That's not the physician who did the surgery. That's the guy.
7 years ago, Joe had brain surgery to allay the effects of severe epilepsy. fiber system, the corpus callosum, is located midway between the two hemispheres. When it was surgically severed in Joe's brain, the transmission of information between the two hemispheres was halted. Michael Gazaniga.
What we can do is play tricks by putting information into the disconnected, mute, non-talking right hemisphere and watch it produce behaviors. And out of that, we can really see that there is, in fact, a reason to believe that there's all kinds of complex processes going on outside of his conscious awareness of his left half brain.
Well, I'm going to show you some things. I just want you to tell me what you see. And here we go. You ready? Look right at the top.
There's something he might not explain that you need to know, which is that signals cross when they come in from the eye. Why this occurs in the course of evolution, I'm not entirely sure, but it does. So the right part of your brain gets signals from your left eye. The left part of your brain is processing signals from the right eye. And I have actually meant to say this. The hemispheres are specialized. So for most people, in most cases, the left hemisphere does much, much more of the action that is language and math. So language and math in some ways are kind of related. There's a symbol system. There's rules for the order in which the symbols should appear. If you jumble them up, you change the, there's some kind of logic that's related to both of them. Whereas if you are imagining holistically an image, if you do one of these mental rotation tasks that we saw, where you see something and imagine what it looks like turned like this, much more of the action is occurring in the right hemisphere. So sorry I didn't put this up earlier. So what you're about to see requires those two facts. The hemispheres are not identical, and right from out there goes to left. This is true for eyes and ears, and left goes to right. Okay, so car on the right, he says it says car because it's processed on the left. No problem at all for him.
When Joe focuses on a point, everything to the right of the point goes to his left brain, the dominant hemisphere for language and speech. So we can see here that when we flash a word or a picture, Joe is easily able to name it. Close your eyes and let your left hand do a little work here.
So that was pan. We know it can't be that he doesn't know that word. Pan flashes up. Pan flashes up on the left, so it goes to the right part of the brain, and he can't say pan because the language processing is on the left. So there's two possibilities. One, of course, is that he, in essence, never saw the word pan and nothing happens, but instead, okay, drew more of a pot, but really,
Now, when a word or a picture falls to the left of a fixation point, that information goes to his disconnected right half brain. And as we can see here, Joe is unable to name it. Joe is able to draw the picture with his left hand, the left hand getting its major control from the right half brain.
that's so good, I'll risk blowing it and do this again.
That information goes to
Okay, that was car on the left, tire right on the right, or wheel on the right. So if you ask him, what did you see? He says, wheel. And then if you ask him to draw a picture of what he saw,
And as we can see here, Joe is unable to name it. Joe is able to draw the picture with his left hand, the left hand getting its major control from the right half brain. Who do you know?
Okay.
What do you see?
Wheel. 1 second. Go 1 second.
So even though he can't name it, his left hand is able to draw out the picture of the stimulus of the picture or word that we presented to his right half brain. What did you see? So just close your eyes and draw with your left hand. Just let it go. Nice, what's that?
Soft.
Just a dramatic example of a neurologic case that really allows you this window into the non-conscious.
Oh, there are many cases where the person comes up with an answer. Why'd you draw that? And then, you know, the people, Gazzaniga and others doing these experiments, oh, I really like saws. I was just thinking of chopping up some wood at home. And the person essentially confabulates some wacky answer because they're completely unaware that they had seen a saw.
So if he can't necessarily say what he saw, does he mumble something, or he just doesn't have the ability to say anything at all?
The reports are that he has no ability to say anything at all. At one point, he mumbled something, but he was mumbling what had come in from the right. Right. The reports are, if the corpus callosum is totally cut, he's supposed to be totally unable to report at all. That's, I mean, obviously, I've never been in the room during the studies, but the reports are absolutely cannot report at all. I assume the person could sort of learn eventually about his condition and then make the inference that I must have seen a saw, but it would be like that. It would be literally like remembering, oh, I must have been at this place, but I've totally forgotten because I was 1 year old, but I saw this picture when my family went on this trip to the Upper Peninsula, so I guess I was there.
Sorry. Why does he not realize that, oh, I'm drawing a saw, not a hammer? What happened?
Yeah, I don't know. I was thinking that right. It's funny that it's hard to read the phenomenology of this thing, so I have no real answer. Right, but I have the same. It seems like the person would do the sort of backwards inference. Oh, I did this. I must have been one of these studies. There's a guy with a camera, Michael Gazzaniga. I know I had the split brain thing. Yet there's something so overwhelming. You know, what if I told you right now, it's just a few seconds ago, there was a horse in front of you. It's this crazy idea. It would be much simpler if you suddenly were thinking of a horse to think that, oh, well, you know, I saw a horse race on TV. The notion that you saw there was a horse standing here and you don't remember, and it was a few seconds ago, this is, I'm not just totally making this stuff up. This kind of thing is what Gazzaniga and others say, that essentially once after the stimuli are presented, the person is working in a normal world. Oh, I wonder what happened here. The inference, I saw, there was something here, I saw it, but wasn't where I saw it, is so bizarre that at least in the cases I've ever seen on film, though you expect it, that's not where the person goes, and they instead come up with these other strange explanations, very much like, oh, I enjoy saws. You know, I used to play in one of those old bands where they bend the